Hello there, and welcome to The Midnight Scientists. I am so glad you've chosen to spend these next quiet moments with me. Before we begin our journey, if you find a sense of peace in these gentle explorations of science, a quiet like or subscribe is a wonderful, silent way to show your support. It helps our sleepy community grow, and it is as effortless as a slow, deep breath. Now, wherever you are, find your place of rest. Perhaps you're nestled in a cozy bed, the sheets cool against your skin. Or maybe you're reclining on a soft couch, a beloved pet purring gently on your chest. You might even be swaying in a hammock with the vast, silent tapestry of the stars above you. I hope this gentle journey into the heart of the atom will help you to unwind, to breathe a little more slowly, and to let your thoughts soften, floating like motes of dust in a moonbeam, gently into sleep. I'd love to imagine where in the world you might be listening from tonight. It's a beautiful thought, seeing this little community of curious minds stretching across the globe like a quiet, invisible constellation, all of us connected by a shared moment of calm. I do hope this story doesn't prove to be too interesting. You see, it is a delicate balance we seek. If you find yourself awake until the very end, well, you will at least know a great deal more about the atom than when you began. And if you drift away somewhere around the discovery of the electron, that is perfectly fine too. Either way, we are in no rush tonight. This episode is all about whispers, specifically the soft, persistent whispers of the atom. From ancient Greek philosophers dreaming of invisible particles to the ethereal dance of quantum mechanics and its subatomic poetry, we are going to ease our way through more than 2,000 years of ideas, of experiments, of quiet surprises, and occasional muffled explosions. But do not worry. Tonight, there will be no stark lab coats, no tests to be taken, and no jarring alarms. There is only curiosity and calm. So let us take one last deep breath together. Settle in and let us follow the trail of tiny things, things far too small to ever see, yet somehow they hold up the entire universe. And as always, this video is created for relaxation and educational purposes only. It is not intended as medical advice or a substitute for professional care. Long before the hum of particle accelerators and the stark elegance of quantum equations, there were sandals on dusty paths, the rustle of papyrus scrolls, and the endless deep blue sky of the Mediterranean. Here, around 2,500 years ago, Greek thinkers were already pondering questions that still echo in our minds today. What is the universe truly made of? Can something truly become nothing? And if you break a rock in half, and then break that half again and again and again, do you ever reach a piece so infinitesimally small that it cannot be broken any further? Into this sun-drenched world of inquiry stepped a philosopher named Leucippus and his more famous student, Democritus. Together they offered a radical, beautiful answer. Yes, they said, there must be a smallest possible piece of matter. They called it atomoi, a word meaning uncuttable. These atomoi, they imagined, were tiny, eternal building blocks that made up everything, from the stone beneath their feet and the wine in their cups, to the flesh of their bodies and the fire in their hearths. This was not just a poetic metaphor, it was a profound physical claim about the very structure of reality. According to their vision, atoms were solid, indivisible, and varied only in their shape, their size, and their ceaseless motion. Some might be smooth and round, tumbling over one another like polished river stones. Others might be jagged and hooked, catching and clinging to each other. Their collisions and their combinations, they believed, gave rise to all that we see and all that we experience. What's more, Democritus didn't just imagine these tiny particles floating in isolation. He also proposed the existence of the void, a great, silent, empty space in which these atoms could move freely. To a modern ear, this might sound obvious. Of course, things move through space. But at the time, the idea of pure emptiness was deeply controversial. Many believed that nature abhorred a vacuum, that a universe with true nothingness in it was heresy, or at the very least, highly suspicious. Democritus took this invisible world with the utmost seriousness. He believed that even the soul was composed of atoms, special ones, smooth and spherical, that zipped through the body like quicksilver, animating it with thought and feeling. He didn't just theorize atoms for the sake of science. He thought they could explain perception, thought, and even happiness. For Democritus, true knowledge was about aligning the mind with the deeper, invisible patterns of nature. He was said to be so cheerful and confident in his ideas that later writers nicknamed him the laughing philosopher. But not everyone was laughing. While Democritus was imagining a universe of atoms and voids, other powerful thinkers were casting a far more skeptical gaze. Plato, for instance, was not fond of the atomist's stark materialism. He preferred to believe in ideal forms, perfect, abstract blueprints that existed in a realm beyond the physical world. Reality, in his view, was just a fuzzy, imperfect imitation of these higher truths. The notion that everything could be reduced to spinning lumps of matter didn't quite fit with his more spiritual and mathematical worldview. Then there was Aristotle, whose influence would dominate Western science for nearly 2,000 years. Aristotle rejected the idea of the void outright. He believed that nature was continuous, a seamless fabric, not composed of discrete particles separated by emptiness. Instead of atoms, he proposed that all matter was a blend of four fundamental elements: earth, air, fire, and water. These were not made of smaller parts, but were forms shaped by four essential qualities: hot, cold, wet, and dry, constantly transforming one into another. Rather than a mechanical universe of bouncing particles, Aristotle imagined a world filled with purpose and essence, with everything striving toward its natural, proper place. Aristotle's vision was elegant, intuitive, and most importantly, easy to teach. His writings were meticulously preserved, copied, and revered long after the works of Democritus had faded into the dust of forgotten libraries. In fact, not a single complete work of Democritus survives to this day. What we know of him comes mostly from quotes and summaries written by others, many of whom did not agree with him. And yet, there is something so enduring, so resonant about the atomic idea. It may have been pure speculation, but it was startlingly modern. At a time when most explanations relied on the whims of gods or metaphysical forms, the atomists tried to explain the world in purely physical terms. No divine puppeteers, no magical essences, just tiny bits of stuff moving through silent space. Even their metaphors were ahead of their time. They imagined atoms as constantly in motion, swirling like dust motes dancing in a sunbeam. They believed the differences in materials, why iron is hard and honey is sweet, came from the shape and arrangement of the atoms themselves. That is not so far from how we understand things today. Of course, none of it was based on experiment. There were no microscopes, no chemical analyses, no data or diagrams. This was a philosophy of pure deduction and imagination, not measurement. But sometimes, imagination gets surprisingly close to the truth. The atomists laid down a conceptual foundation that would echo through history,
quietly waiting for the tools that could finally test it. It's tempting to romanticize these early thinkers as lonely geniuses, staring at the sea and dreaming of molecules. But they were also part of a lively intellectual ecosystem. Greek city-states were buzzing with debates, lectures, and wandering philosophers. Ideas spread via ship and scroll, and disagreements were as common as olives. What mattered wasn't just having a theory, it was defending it, arguing it, refining it. Democritus and Leucippus may not have won the popularity contest in their own time, but they left behind a remarkably resilient idea that everything, your hand, the stars, the very air between them, might be made of the same tiny, indivisible stuff. An idea that would soon vanish into history's shadow for many long centuries, only to rise again with an unexpected and undeniable force. And so, nestled within ancient Greece, among stone temples and philosophical squabbles, a whisper began. A whisper that the universe, for all its grandeur, might be made of invisible pieces dancing through the void. After Democritus and Leucippus whispered their ideas about atoms into the ancient world, the universe went oddly quiet on the subject. Not because the idea was disproven, but because, for most people, it simply wasn't useful. For nearly 2,000 years, the atom would retreat into the background, a forgotten dream, while other theories about the nature of matter took center stage. Most of them shimmering with a curious mix of mysticism, philosophy, and a faint touch of sulfur. This was the era of alchemy. Not chemistry, not yet, but its strange and symbolic ancestor. Alchemy was a curious blend of experimentation, spirituality, and metaphor, practiced across the Islamic world, medieval Europe, China, and India. It was part science, part philosophy, and part a quest for personal transformation. The most famous goal of the alchemists, of course, was the transmutation of base metals, like lead, into pure gold. But that was only the shiny surface of a much deeper pursuit. Alchemy was also about purification, immortality, and understanding the hidden essences of things. The alchemists weren't entirely wrong in wanting to transform matter. In a way, they sensed that materials could change form, combine, separate, and evolve. Ideas that would eventually become central to modern chemistry. But lacking the tools of today, they worked with intuition, patient observation, and deeply symbolic systems. Instead of atomic weights and periodic trends, they had elaborate diagrams, mystical correspondences, and an enduring faith in the number 4. Ah, yes, the number 4. For many centuries, matter was explained through the lens of the 4 classical elements: earth, air, fire, and water. This framework, inherited from Aristotle and refined through various traditions, dominated Western and Islamic thought alike. These elements weren't considered atoms or particles, but rather fundamental types that made up all things. Wood, for example, might be seen as mostly earth with a bit of fire, while steam might be seen as mostly air with a splash of water. Everything was a cocktail of these elements, shifting and transforming in response to heat, moisture, and the occasional celestial alignment. It might sound quaint now, but it wasn't an entirely foolish idea. The concept that matter is composed of fundamental types, trying to balance and interact, is not so far removed from how we think about elements today. The difference, of course, is that modern chemistry classifies matter based on its atomic structure, not on how damp or dry it seems. Still, in the absence of microscopes and molecular models, the 4-element theory provided a surprisingly flexible way to explain the world. You could use it to interpret illness, weather, moods, and metallurgy, all in one go. The influence of Aristotle loomed large in all of this. His rejection of the void meant that the idea of atoms floating through empty space had little traction. And because Aristotle's works were so influential, especially once adopted by medieval scholars, the atomic idea was largely shelved in favor of more continuous, qualitative models of matter. Add to that the philosophical discomfort with imagining invisible particles, and atoms found themselves exiled from respectable thought. But even as atomic theory lay dormant, something important was happening quietly in the wings. People were starting to sort and classify substances. Alchemists and early natural philosophers began documenting the properties of different metals, minerals, and acids. They observed how substances reacted, combined, and changed color. Though they lacked a unifying theory like atomic structure, they were gathering data, sometimes muscly, often poetically, but data nonetheless. In the Islamic Golden Age, scholars such as Jabir ibn Hayyan, often Latinized as Geber, advanced alchemical practice by systematizing it. Jabir is credited with developing early forms of distillation, crystallization, and evaporation. He believed that all metals were composed of different proportions of mercury and sulfur, a theory that wasn't quite right, but it edged closer to the notion that different materials have distinct internal structures. Then later in the European Renaissance, alchemists like Paracelsus brought their own flair to the field. Paracelsus introduced the idea that chemistry could be used to treat disease, shifting the focus from gold making to medicine. He also expanded the elemental system by introducing salt as a third principle alongside sulfur and mercury. Not the table variety, but a symbolic essence of solidity and fixation. Alchemy was growing more complex with its own language, rituals, and an increasingly experimental attitude, though still wrapped in mystery. Despite the mystical overtones, these early practitioners were developing lab techniques and chemical processes that would eventually prove invaluable. Glassware evolved, reactions were cataloged, mixtures were separated. The idea of transformation was being explored not just symbolically, but practically. In the East, Chinese alchemy had its own rich history, often tied to Taoist philosophy and the search for immortality. Practitioners worked with cinnabar, mercury, and other substances believed to grant longevity or enlightenment. Although the spiritual goals differed, Chinese alchemists also observed chemical reactions and changes in matter, contributing to the broader human understanding of material transformation. So while the atomic model gathered dust, the world didn't stand still. Through hands-on work, accidental discoveries, and the occasional philosophical detour, people were gradually assembling a patchwork understanding of substances and how they behave. The atom wasn't back in the spotlight yet, but the stage was quietly being set.
Looking back, it's easy to smile at the idea of lead turning into gold or an elixir granting eternal life. But within those ambitious dreams was a deeper yearning to understand the fundamental nature of matter and life. Alchemists believed that the world held secrets, and that through careful observation, symbolic reasoning, and maybe a little luck, those secrets could be unlocked. In their own way, they were listening for whispers too, just not yet from atoms. For almost 2 millennia, then, the atomic theory slumbered. It hadn't been disproven, it had simply been set aside in favor of more immediate, intuitive frameworks. Matter was changeable, mysterious, and filled with essence and purpose. Invisible particles had little room in a universe built on qualities, humors, and hidden correspondences. Still, here and there, in smoky labs and on handwritten notes, glimmers of structure began to appear. The tools were crude, the theories fuzzy, but a slow, steady curiosity kept inching forward. It was only a matter of time before someone, somewhere, would dust off the ancient idea and ask the question anew. What if everything really is made of tiny, invisible things? By the 17th century, the ancient model of air, fire, water, and earth was beginning to show cracks. Curious minds across Europe were poking, heating, sealing, and occasionally exploding things in their quest to understand what the world was truly made of.
And one of the great puzzles that caught their attention was air. This invisible, seemingly weightless substance that filled the space around them. What was it, exactly? Was it a kind of nothing? Or was there more to it than met the eye? Turns out there was a lot more. At the center of this intellectual gust was Robert Boyle, an Irish natural philosopher with a penchant for careful measurement and a surprisingly robust tolerance for unpleasant smells. Boyle didn't buy the classical idea that air was simply an ethereal essence. To him, air was a substance, a real physical something that could be weighed, compressed, and studied. With the help of his friend and collaborator, Robert Hooke, he built elaborate air pumps and began experimenting with vacuum chambers. Now, to appreciate just how revolutionary this was, imagine a world where people weren't even sure a vacuum could exist. Aristotle, still clinging tightly to the intellectual stage, had declared that nature abhors a vacuum. But Boyle, ever the curious skeptic, decided to find out for himself. When he removed the air from a chamber using his pump, he noticed some fascinating things. Candles went out, animals struggled to breathe, and the usual sounds of life vanished into an unnerving silence. Whatever air was, it wasn't nothing. It had substance, it had power. Boyle and Hooke's experiments helped usher in the idea that air was made of particles, tiny bits of matter with space between them. These particles could move, collide, and push against the walls of a container, and that pressure, they found, changed depending on how much space the particles had to move in. Squeeze the container and the pressure rises. Let it expand and the pressure drops. This wasn't just a fun party trick with bell jars. It was the beginning of a profound shift in thinking. Boyle formalized the relationship between pressure and volume into what's now known as Boyle's law. If the temperature remains constant, the pressure of a gas is inversely proportional to its volume. In other words, if you halve the volume, you double the pressure. It was one of the first mathematical laws to describe how matter behaves in a measurable, predictable way. And unlike earlier philosophical theories, Boyle's work was grounded in repeatable experiments. He wasn't just speculating about the invisible, he was measuring its effects with instruments and equations. This was a major turning point. Science was beginning to pull away from metaphysical musings and move toward empirical, testable knowledge. Instead of imagining what air might be, Boyle and his colleagues were capturing it in glass tubes and making it do tricks on command. Robert Hooke, meanwhile, was no mere assistant. A polymath with a sharp mind and a sometimes sharper temper, Hooke made contributions that ranged from biology to architecture. In the world of gases, he played a key role in refining the air pump and conducting experiments that showed how living creatures depended on air. He even proposed early ideas about combustion and respiration, suggesting that something in the air was consumed in both processes, a hint, perhaps, of oxygen, though that discovery would come later. What really began to click in this period was the realization that gases behave like matter in motion. Rather than treating air as a uniform, ghostly substance, scientists started to think of it as a swarm of tiny particles zipping around and bouncing off surfaces. These movements could explain pressure, temperature, and even the behavior of different gases under different conditions. The idea of particles in motion wasn't entirely new. Democritus would have smiled. But now it was being backed up with tools, math, and experiment. Air was not an invisible magical element. It was a dynamic collection of particles, and those particles obeyed rules. Boyle also took great care to distance himself from alchemical traditions. He famously wrote The Skeptical Chemist, a book that questioned the traditional elemental framework and argued for a more modern, analytical approach. In it, he proposed that substances were composed of corpuscles, or small bits of matter, which combined in various ways to form the materials we observe. It was a kind of proto-atomic theory, still speculative, but more grounded than the old symbolic models. One of the beautiful things about this period is that science was still half experiment, half theater. Imagine candlelit labs filled with bubbling flasks and brass instruments, with curious gentlemen in powdered wigs debating over whether air had weight. Spoiler alert, it does. Boyle demonstrated this by trapping air in containers and comparing their weights on a scale. That was a big deal. Until then, many believed that since air was invisible, it must be weightless. Not so. As more scientists joined the fray, gases began to reveal their secrets. Hydrogen, oxygen, nitrogen, all these components of air would eventually be isolated and named. But for now, the key insight was simply that air was something that could be compressed, measured, and crucially, understood. And just like that, the study of matter began to evolve into something sharper, cleaner, and more quantitative. Instead of mystical essences and symbolic correspondences, people were working with pressure gauges, barometers, and air pumps. Chemistry was starting to stretch its legs, ready to walk away from its alchemical adolescence and step into a more experimental adulthood. By showing that even something as invisible as air had structure and behavior, Boyle helped lay the groundwork for modern chemistry and physics. He didn't solve all the mysteries of matter, but he cracked the door open just enough for the light to get in. And once people realized that even something as invisible as air had structure and behavior, it was only a matter of time before they'd turn their gaze to other, even smaller things. In the bustling streets of 18th century Paris, amid powdered wigs, philosophical salons, and the distant rumble of revolution, a man named Lavoisier was quietly changing the course of science forever. He wasn't chasing gold or a divine elixir. He wasn't dreaming of invisible atoms or wrestling with metaphysical fire. What he was doing with remarkable precision was weighing things carefully, obsessively, and in doing so, he helped transform chemistry from a mystical art into a true science.
Antoine Lavoisier is often called the father of modern chemistry, and not just because he had excellent handwriting or a strong jawline. He brought clarity, structure, and above all, measurement to a field that had been muddled for centuries with vague terminology and loose reasoning. Where alchemists had spoken of phlogiston and essence, Lavoisier spoke of oxygen, mass, and conservation. But to understand how radical that was, it helps to appreciate the scientific mess he inherited. At the time, one of the dominant theories about combustion, how things burn, was the phlogiston theory. According to this idea, every combustible material contained a mysterious substance called phlogiston. When something burned, it was thought to release its phlogiston into the air. A flame, therefore, wasn't a chemical reaction, it was just phlogiston leaving the building. There were some problems with this theory, such as the fact that certain metals gained mass when they were burned rather than losing it, as you'd expect if phlogiston was flying away. But instead of ditching the theory, many tried to explain this away by suggesting that phlogiston had negative weight. Yes, negative weight, like an invisible balloon hiding in your coal. Lavoisier didn't buy it. He had a different approach, one rooted in experimentation and relentless accuracy. He believed that the only way to understand a chemical reaction was to know exactly what went in and exactly what came out. No guesswork, no metaphysical fudge. And so he built himself a laboratory, not just any lab. His was the scientific equivalent of a grand ballroom filled with polished copper instruments, balances sensitive enough to detect the difference in a single grain of sand, sealed glass vessels, and elaborate gas collection setups. He spared no expense, which was convenient since he was also a wealthy tax collector. His wife, Marie Anne, was a brilliant collaborator who not only illustrated his experiments, but also translated scientific papers from English to French and helped edit his work. If you ever imagined chemistry as a solo pursuit of grimy beakers in a dungeon, Lavoisier's gleaming lab would have felt like a breath of fresh, measured air. One of his most important discoveries came from studying combustion more closely than anyone before him. He observed that when a metal like mercury was heated in air, it formed a calx, a powdery substance that we now know is an oxide. But here's the twist. The calx weighed more than the original metal. Instead of assuming that phlogiston had vanished, Lavoisier suspected that something had joined with the metal.
Using closed vessels and carefully controlled air volumes, he demonstrated that a portion of the air was consumed during the process. That missing portion, he realized, was not a void or a loss, but oxygen binding to the metal. From this, he formulated one of the most important principles in all of science, the law of conservation of mass. In a chemical reaction, matter is neither created nor destroyed. It only changes form. Burn a log, and it might seem to vanish, turning to ash and gas. But if you could capture everything, the smoke, the soot, the leftover carbon, the total mass would remain exactly the same. This might sound obvious today, but it was revolutionary at the time. The idea that chemical processes followed precise, accountable rules down to the milligram was a major leap forward. Lavoisier's insistence on measurement did more than just tidy up a few theories. It changed the way chemistry was done. Before him, many reactions were described qualitatively. This powder smells sweet, that one turns blue, this mixture gets warm. Lavoisier pushed for a quantitative approach. How much heat? How much weight? How much gas? Chemistry started to shift from a descriptive art to a mathematical science. Instead of swirling symbols and esoteric labels, Lavoisier called for a new language based on observable facts. And he didn't stop at oxygen. Lavoisier was instrumental in identifying and naming several key elements. He helped establish the modern understanding of hydrogen and nitrogen, and played a central role in compiling the first systematic list of elements. Gone were the days of earth and fire. Now there were real substances, each with measurable properties and predictable behaviors. In 1789, he published the Traité élémentaire de chimie, elementary treatise of chemistry, which many considered the first modern chemistry textbook. It introduced a systematic chemical nomenclature and clearly outlined chemical reactions using equations. It's hard to overstate how much this book changed the game. For the first time, chemistry students could learn from a structured, logical system rather than being handed a mysterious collection of symbols and recipes. He also coined the term oxygen from the Greek for acid former, based on his ultimately incorrect belief that all acids contained oxygen. Not every guess was perfect, but his overall method, observe, measure, repeat, was solid gold. There's a poetic irony to Lavoisier's life, because while he brought order and reason to the science of matter, the world around him was descending into chaos. The French Revolution was gathering steam, and Lavoisier's role as a tax collector made him a target. Despite his scientific fame, he was arrested and sentenced to death. In 1794, at the age of 50, he was executed by guillotine. The mathematician Joseph Louis Lagrange remarked afterwards, "It took them only an instant to cut off that head, and 100 years may not suffice to produce another." Lavoisier's death was a tragic loss to science, but his work endured. His approach set the stage for generations of chemists to come. The laboratory became a place of precision, not potions. Reactions were balanced like equations. Substances were named, classified, and tested. Matter had rules, and those rules could be learned, tested, and taught. Most importantly, he gave us confidence that the physical world could be understood through careful observation, that you could weigh air, count invisible gases, and find order in the flicker of a flame. Through his experiments, matter began to feel real in a way it hadn't before. Not just the stuff of dreams or elements, but measurable, quantifiable, knowable. Lavoisier didn't invent the atom, but he carved a path straight toward it. By insisting that every chemical process followed the same laws, no matter how dramatic or subtle, he helped lay the intellectual foundation for seeing matter as a system of parts and patterns. In the glow of his laboratory lamps, weighed on brass ales and sealed in glass, the chemistry of the future had quietly begun. In the misty hills of early 19th century England, where factories were multiplying and chimneys coughed coal smoke into the sky, a quiet school teacher named John Dalton was busy resurrecting a 2,000-year-old idea. He wasn't doing it with flashy experiments or fiery demonstrations. No explosions, no dramatic lectures, just notebooks, numbers, and a deep fascination with the invisible.
Dalton, born in a modest village in Cumbria in 1766, was the kind of scientist who liked to count things. He had a passion for measuring the world and a deep love for dry precision. As a Quaker, he wore plain clothes, spoke plainly, and lived plainly. But his ideas were nothing but plain. He started his scientific career studying the weather. Obsessed with clouds and pressure, he recorded thousands of weather observations, one raindrop at a time. But in trying to understand the atmosphere, Dalton became deeply interested in gases, not just their behavior, as Boyle had explored, but what they were made of. Why did different gases behave so differently from each other? Why didn't they all mix in evenly like tea and sugar? Dalton noticed that when gases like nitrogen and oxygen were present in the same space, they didn't always blend into a uniform fog. They stayed oddly distinct. He began to wonder, maybe these gases weren't smooth and continuous. Maybe they were made of tiny, separate particles, particles that had weight, particles that were different from one gas to another. In short, maybe Democritus had been right all along. What Dalton did next was both bold and beautifully logical. He revived the ancient idea of atoms, but this time he brought data, lots of data. Dalton proposed that all matter is made of indivisible atoms and that all chemical elements are composed of their own unique kind of atom. Hydrogen atoms are not the same as oxygen atoms. Sulfur atoms are different again. These aren't just philosophical particles floating through the void, they're specific, measurable entities with real weight and behavior. Even more importantly, Dalton introduced the idea of atomic weight. He proposed that each type of atom has a specific mass, and that chemical reactions are simply rearrangements of these atoms. When two elements combine, their atoms form compounds in fixed whole number ratios. For example, one atom of hydrogen might combine with one atom of oxygen, or two, or three, but never with half an atom. It was like the chemistry version of Lego, with atoms snapping together in predictable, countable ways. This idea helped explain why compounds always contain the same proportions of elements. Water, for instance, always has the same ratio of hydrogen to oxygen. It's not a coincidence, it's arithmetic. Dalton showed that this wasn't just a curious pattern, but a fundamental truth about how atoms behave. To make these ideas easier to understand, Dalton began drawing little circles to represent atoms. He used different symbols to represent different elements: a plain circle for hydrogen, a circle with a dot for oxygen, a circle with a cross for iron, and so on. It was simple, almost childlike, but profoundly effective. These were the first atomic diagrams in modern science, a symbolic language for the invisible world. His diagrams and ideas were published in 1808 in a book called A New System of Chemical Philosophy. The title wasn't exactly catchy, but the contents were revolutionary. Chemists now had a framework for understanding why substances combined the way they did. It wasn't alchemical whim or elemental essence, it was atomic ratios and mass. Dalton's atomic theory rested on a few basic postulates. First, all matter is made of indivisible atoms. Second, all atoms of a given element are identical in mass and properties. Third, compounds are combinations of different kinds of atoms. Fourth, chemical reactions involve the rearrangement of atoms, not their destruction. And fifth, atoms cannot be created or destroyed in a chemical reaction. Some of these ideas would eventually be revised. It turns out atoms can be split, and isotopes mean not all atoms of an element are truly identical. But for the early 19th century, this was a stunningly useful model. It made chemistry predictive, not just descriptive. Dalton's work didn't just explain what chemists were already observing, it gave them a way to organize it. By assigning weights to atoms and identifying how they combined, he laid the groundwork for something extraordinary, a deeper classification of elements.
Soon, other chemists began to adopt and refine his ideas. They improved the accuracy of atomic weights, developed better techniques for isolating elements, and started noticing patterns. Certain elements had similar properties. Some reacted the same way. Others seemed to repeat at regular intervals when listed by mass. The periodic nature of elements was slowly coming into focus. Dalton didn't live to see the full emergence of the periodic table, but his atomic theory lit the path that led to it. By giving atoms distinct identities, he transformed chemistry from a messy collection of recipes into a rational science. Elements became more than just names in bottles. They were defined by their atomic character, their weight, their bonds. It's worth noting that Dalton wasn't a celebrity in his time. He never held a prestigious academic post. He kept teaching at a small Quaker school in Manchester and continued his meteorological observations until the end of his life. But his ideas quietly reshaped the world. Today, every chemistry student learns about atomic weights, molecular ratios, and Dalton's laws of proportion. They may not know that he also studied colorblindness, now sometimes called Daltonism, or that he was terribly fond of long walks. But they know his dots. His little atomic sketches launched a revolution, not with a bang, but with a scribble. Perhaps the most charming thing about Dalton was his devotion to logic. He didn't invent atoms because it was fashionable. In fact, most scientists at the time still preferred more fluid theories of matter. But Dalton, armed with his experimental results and a stubborn sense of reason, followed where the numbers led. If matter behaved in consistent ratios, there had to be a reason. If different elements combined in simple whole numbers, there had to be a pattern, and that pattern, he believed, was made of atoms. The power of his theory lay in its beautiful simplicity. It explained chemical reactions without needing mysterious forces or hidden fluids. It treated substances like puzzles made from tiny parts, parts that you could count, weigh, and rearrange. For the first time, matter wasn't just observed, it was modeled. It had structure. It had math. Dalton's world was still one of hand-blown glassware and flickering lamps. There were no electron microscopes, no lasers, no particle accelerators. But even without ever seeing atoms, he showed us how to think about them. His ideas were clear enough to hold, small enough to picture, and solid enough to build on. And so, thanks to a quiet teacher with a sharp pencil and a sharper mind, atoms became more than a whisper. They became a language, a way to describe the universe one particle at a time. In the snowy heart of 19th century Russia, wrapped in furs and surrounded by stacks of chemical data, Dmitri Mendeleev was doing something unusual for a scientist. He was playing a kind of intellectual solitaire with the elements. It was the late 1860s, and chemistry was still a bit of a wild west. Scientists had discovered dozens of elements by now, but the list was messy, an ever-growing collection of substances without clear relationships or structure. It was like owning a dictionary where the words were tossed in at random. And Dmitri Ivanovich Mendeleev, with his thick beard and sharper-than-average curiosity, decided to bring order to the chaos. Dmitri Ivanovich Mendeleev was no stranger to perseverance. Born in a small Siberian town in 1834, the youngest of at least 14 children, yes, 14, he was raised in the kind of environment that breeds either despair or relentless determination. He chose the latter. After his father lost his sight and passed away, and his mother's glass factory burned down, his mother still managed to get him to university by dragging him across the country. Literally, she took him by horse and carriage from Tobolsk to St. Petersburg so he could enroll in school. As far as supportive parenting goes, that's a hard act to follow. By the time he became a professor, Mendeleev was deeply immersed in the puzzle of the chemical elements. More and more were being discovered, but their relationships remained unclear. Some elements behaved similarly to others, Lithium, sodium, and potassium all reacted violently with water, for example, but nobody had found a master key to explain the patterns. Some tried grouping them by atomic weight, others looked at reactivity, but the arrangements were inconsistent and left a lot of questions hanging. Mendeleev had a different strategy. He approached the problem like a card game. In fact, he used actual cards, one for each known element, on which he wrote the element's properties, atomic weight, chemical behavior, density, and more. Then he shuffled and arranged them over and over, searching for a pattern that made sense. It was like a scientific version of Tetris, only with hydrogen and chlorine instead of blocks. Eventually, a remarkable rhythm began to emerge. Mendeleev noticed that if he arranged the elements in order of increasing atomic weight, certain properties repeated at regular intervals. Soft metals, reactive halogens, noble gases, they all showed up in a kind of musical loop. It was as though the elements were singing in harmony, each voice returning after a predictable number of steps. This led him to construct what would become known as the periodic table, a grid where elements were placed not just by weight, but by their chemical behavior. Elements in the same column or group shared similar properties. The alkali metals formed one family, the noble gases another, and the transition metals marched across the center like a well-trained army. But Mendeleev didn't stop there. He noticed something even more profound. Some elements didn't quite fit the pattern if arranged strictly by atomic weight. Instead of forcing them into awkward spots, he moved them boldly. He swapped elements like tellurium and iodine, even though their weights were out of order, because their properties lined up better that way. This was a risky move. It meant trusting the pattern more than the numbers, but it paid off. Most impressively, Mendeleev left deliberate gaps in his table, empty spaces. These weren't mistakes, they were predictions. He boldly declared that elements should exist in those spaces, even though nobody had discovered them yet. And he didn't just shrug and move on. He described the properties those missing elements would likely have, their weights, densities, oxides, and affinities. One such predicted element, which he called Eka aluminum, Eka meaning one beyond in Sanskrit, would later be discovered and named gallium. Its properties matched Mendeleev's forecast almost perfectly. Another, Eka silicon, turned out to be germanium. One by one, the gaps in his table were filled, not by guesswork or luck, but by the structure he had seen hiding in plain sight. This predictive power gave the periodic table a credibility few scientific models ever achieve. It wasn't just a retrospective summary, it was a forward-looking map of the elemental world. Mendeleev had turned chemistry into a guided tour rather than a scavenger hunt. At first, not everyone was convinced. Many chemists were skeptical of the rearrangements and the empty spaces. But as the predicted elements were discovered and their properties matched the forecasts, Mendeleev's reputation soared. He had done what no one else had managed. He brought a deep and elegant order to the fundamental building blocks of matter. What's particularly charming about Mendeleev's approach is how intuitive it was. He didn't start with a grand theory or a complex formula. He started with index cards, careful observation, and a refusal to give up on the idea that nature must have some kind of logic. He believed the elements were telling a story, and he was determined to listen until he could understand the plot. Of course, Mendeleev wasn't working with the modern understanding of atoms. The concept of protons and electrons hadn't yet been nailed down. He didn't know about atomic number, the count of protons that uniquely identifies each element. That would come later. But his faith in the periodicity of properties was strong enough to override even the official numbers. And when atomic number was eventually discovered, it turned out to explain why the table worked. It wasn't atomic weight that determined placement, but atomic number. And Mendeleev had, through intuition and logic, gotten it mostly right anyway. Beyond his contributions to chemistry, Mendeleev was a bit of a polymath. He worked on everything from oil refining to agricultural reform to the standardization of vodka. He even tried to devise a unified theory of everything, though that part didn't quite pan out. Still, his versatility reflected the same spirit of curiosity that made his table possible. He wanted to understand how things fit together, whether they were atoms, molecules, or economic policies. Mendeleev's periodic table is now taught in every chemistry classroom around the world. It has grown and evolved over time. New elements have been discovered, new rows added, but the bones of his structure remain. It's a rare scientific creation that still stands strong over 150 years after its invention. The table has become not just a reference, but a symbol of scientific order, predictability, and beauty. There is something deeply satisfying about the idea that the universe has a rhythm and that we can learn to hear it. That the elements, those raw ingredients of stars and stones and soup, can be arranged into a coherent pattern that stretches across time and space. Mendeleev didn't just give us a way to memorize chemical facts, he gave us a way to see them, lined up like dancers in a cosmic waltz. And it all started with a game of cards, a stack of notes, and a refusal to accept that nature could be so disorganized. In a world growing more complex by the day, Mendeleev showed that even the smallest pieces can reveal a grand design if you're willing to look closely, trust your instincts, and maybe shuffle the deck once or twice.
By the late 19th century, atoms had settled comfortably into the role of fundamental building blocks, indivisible, solid, and reliable. Dalton had given them mass and identity, and Mendeleev had organized them into a neat, elegant table. Chemists and physicists alike were growing rather fond of the idea that the atom was the final stop on the journey inward. A tidy little sphere, behaving itself politely, forming bonds and reactions without too much fuss. And then, something strange began to flicker out of glass tubes and into the minds of puzzled scientists. A curious, ethereal, glowing beam, seemingly emerging from nowhere and refusing to follow the rules. These were the cathode rays, and they would crack open the atomic world in ways nobody saw coming. Cathode rays first showed up in experiments with vacuum tubes, sealed glass chambers from which most of the air had been removed. When a high voltage was applied between two metal electrodes inside the tube, a mysterious greenish glow appeared. The glow always seemed to originate from the negative electrode or cathode and shoot across the tube in a straight line. These rays could make fluorescent materials light up, cast shadows, and even spin tiny paddle wheels placed in their path. Clearly, they weren't just light. They had momentum. They were something. But what? Exactly. Some scientists thought the rays were a kind of wave, maybe a strange light wave bouncing around inside the tube. Others suspected they were particles. But if so, particles of what? Atoms were supposed to be indivisible, whole, unbreakable units. What kind of particle could come out of one? Enter Joseph John Thomson, or JJ to his colleagues, a Cambridge physicist with a brilliant mind and a delightfully understated demeanor. Thomson didn't set out to shatter the atomic model. He was just trying to understand the behavior of these curious rays. But as it often goes in science, a simple question turned into a revolutionary discovery. Thomson's key insight came from bending the rays. He built an apparatus that allowed him to apply electric and magnetic fields to the beam of cathode rays. If the rays were made of charged particles, then the fields should deflect them. And they did, beautifully. The rays curved under the influence of the fields, just as a stream of charged bullets would. From the degree of deflection, Thomson was able to calculate something extraordinary: the ratio of the charge of these particles to their mass. And the result was astonishing. These particles were about 2,000 times lighter than a hydrogen atom, the lightest known atom at the time. That meant they couldn't be atoms at all. They were something inside the atom, something smaller and clearly charged. Thomson had just discovered the electron. It was the first subatomic particle ever identified, and it completely shattered the idea of the atom as indivisible. The solid sphere was no longer so solid after all. The atom had an inner life, a structure. There were bits within it, and those bits could move. To explain this strange new reality, Thomson proposed a model of the atom that looked, well, a bit like dessert.
He imagined the atom as a kind of soft, positively charged sphere, like a cake or a cloud of pudding, with the negatively charged electrons embedded throughout, like raisins. This became known as the plum pudding model, a name that stuck despite sounding like something from a Victorian cookbook. It was a strange image, but it made sense at the time. If atoms were electrically neutral, and now we knew they contained negatively charged electrons, then there had to be some positive charge in there too to balance things out. Thomson's model pictured this positive charge as a kind of diffuse goo, with the electrons floating in it like fruit in jelly. Not everyone was thrilled about comparing atoms to pudding, but the model had real strengths. It accounted for the existence of electrons, it explained why atoms didn't have an overall electric charge, and it introduced for the first time the idea that atoms could have internal parts, discrete entities with their own properties. This was a huge shift. For over 2,000 years, atoms had been considered the most fundamental bits of matter. You couldn't go smaller. You couldn't look inside. But here was a Cambridge physicist saying quite cheerfully that not only could atoms be split, but they had structure, complexity, and behavior. The atomic world had cracks, and in those cracks, the light of new understanding was beginning to shine. Of course, the plum pudding model wouldn't last forever. It had its flaws. It couldn't explain how atoms emitted light. It couldn't account for the full range of observed phenomena in chemical reactions. But it served a crucial purpose. It opened the door. Once electrons were discovered, scientists began to wonder what else might be hiding inside the atom. If there were negatively charged particles, where was the positive charge located? Was it really spread out like pudding, or was it more concentrated? Was there a center? Were electrons just floating, or did they move in patterns? But before the atom could be rebuilt, it had to be broken open. And that's what the cathode ray experiments did. They cracked the shell of the atom, showing that the neat, indivisible spheres of Dalton's world were in fact teeming with motion and mystery. Thomson's work didn't stop with electrons. He went on to explore ions, isotopes, and mass spectrometry, making vital contributions to fields that hadn't even been named yet. He was knighted, awarded a Nobel Prize, and eventually became the president of the Royal Society. Not bad for a man who had once struggled with mathematics and almost became a railway engineer. And perhaps the most poetic part of the story, one of Thomson's students, a young physicist named Ernest Rutherford, would go on to propose an entirely new model of the atom, one that left the plum pudding behind in favor of orbits and nuclei. But even Rutherford never forgot the importance of his mentor's work. Without Thomson's electron, there would be no need to rethink the atom in the first place. The discovery of the electron was like opening a trap door in the floor of physics. Suddenly, there was a whole new level of reality beneath our feet, a level where particles zipped and spun, where charges clashed and combined, where mass and energy played by strange new rules. The atom was no longer the final answer. It was the beginning of a deeper question. And it all started with a flicker in a glass tube, a ray from nowhere, carrying with it the hint that even the smallest things might not be so simple after all. Picture this. It's the early 1900s, and you're in a lab with sheets of gold so thin they're practically see-through. A mysterious radioactive source sits on the table, and an idea is in your head that atoms are like a cosmic dessert, soft blobs of positive charge with electrons floating inside like raisins. That was the state of atomic theory, courtesy of J.J. Thomson's plum pudding model. Now, enter Ernest Rutherford, a New Zealand-born physicist with a booming voice, a taste for bold ideas, and a fondness for smashing things to see what happens. Rutherford had already made a name for himself exploring radioactivity, but now he had a new question. What does the inside of an atom really look like? To find out, he designed one of the most famous experiments in all of science. It was elegant, simple, and utterly explosive in its implications. Rutherford and his colleagues, Hans Geiger and Ernest Marsden, fired tiny particles called alpha particles at an ultra-thin sheet of gold foil. Alpha particles, for reference, are positively charged and relatively hefty as subatomic particles go, more like bowling balls than ping pong balls. According to the prevailing model, those alpha particles should have zipped straight through the gold like peas through fog. After all, the plum pudding atom was supposed to be a soft, diffused cloud of positive charge, offering little resistance. So imagine everyone's surprise when some of those alpha particles didn't pass through at all. A few bounced back, not just deflected a little, but bounced straight back toward the source. Rutherford famously compared it to firing a cannonball at a piece of tissue paper and having it ricochet. The team was stunned. These weren't rare flukes either. While most of the particles passed through as expected, a measurable number were deflected at large angles and some even reversed course. Something inside the atom was solid, dense, and powerful enough to knock an alpha particle off its path. This changed everything. From these surprising results, Rutherford proposed a bold new model. Atoms weren't squishy balls of pudding. They were mostly empty space, with almost all of their mass concentrated in a tiny central region, which he called the nucleus. This nucleus, he reasoned, must be positively charged since it repelled the positively charged alpha particles. The electrons, then, must be whizzing around the central nucleus, held in place by the electric attraction between opposite charges. It was a shocking idea, literally and figuratively. The atom, long considered indivisible and uniform, was suddenly full of structure, and most of it was, in fact, nothing at all. That's right. Almost all the mass of an atom is crammed into an unimaginably small center, while the rest is empty space. If the nucleus of a hydrogen atom were the size of a marble, the electron would be orbiting nearly a football field away. The atom is a ghost with a solid heart. The nuclear model of the atom was born. This shift wasn't just a scientific footnote, it was a revolution. It explained the gold foil results with precision, and it opened up a whole new understanding of atomic behavior. The nucleus, as Rutherford described it, held protons, the positively charged particles he had indirectly discovered through this work. He suspected there might be other particles lurking there too, but that mystery would take a few more decades to unravel. Of course, the nuclear model raised some questions of its own. If electrons were orbiting the nucleus like planets around the sun, what was keeping them from spiraling inward and crashing into it? Classical physics suggested that an accelerating charge, like an electron moving in a circle, should emit energy and lose speed. That would make atoms fundamentally unstable, which clearly wasn't the case. Your face, your tea, and the table beneath it are all holding together just fine. But even with that lingering puzzle, Rutherford's discovery laid the foundation for the next century of atomic exploration. He had peeled back the curtain and shown that the atom wasn't a uniform sphere. It had parts, it had architecture, it had a dense center and distant edges. It was, in essence, a tiny solar system, one where electrostatic forces replaced gravity and particles played cosmic roles on a miniature stage. The experiment itself was a masterclass in simplicity and genius. Using just a radioactive source, gold foil, and a fluorescent screen to detect the flashes of scattered particles, Rutherford and his team revealed the hidden structure of the invisible. They didn't need massive machines or advanced computing, just patience, precision, and a willingness to be surprised. Rutherford himself had a talent for turning that surprise into insight. He was famous for his wit and his insistence on clear thinking. Once, when a student was unsure about a complicated mathematical problem, Rutherford replied, "Don't let me hear anyone use the word can't unless they're talking about the laws of physics." He was a man of conviction and curiosity, a perfect combination for someone digging into the heart of matter. And he didn't stop with gold foil. His later experiments explored nuclear reactions, leading to the discovery that atoms could change their identity by altering their nuclei. In essence, Rutherford cracked open not just the structure of the atom, but the secret of the elements themselves. He laid the groundwork for nuclear physics, atomic energy, and the discovery of new particles. The gold foil experiment marked a turning point. It wasn't just that the model of the atom changed, it was that the way scientists thought about atoms changed. No longer simple and indivisible, atoms were revealed to be dynamic, structured, and most astonishingly of all, mostly empty. The solid world was made of insubstantial things. Tables, trees, and toes were mostly space, stitched together by invisible forces. It's one of the great ironies of physics. The more we zoom in, the more we find absence where we expected substance. But in that absence lies power. The nucleus, tiny and dense, holds nearly all the atom's mass. The electrons, distant and lively, define its volume and behavior. And in between, a vast stillness, like the quiet between stars. Rutherford's model would be refined over time. Others would come along to explain the motion of electrons, the nature of the nucleus, and the rules that governed atomic structure. But the core insight, that atoms have a dense center and are mostly space, remains as true today as it was on the day those alpha particles first bounced off a golden sheet. What began as a simple experiment with some gold foil and a few radioactive specks turned into one of the greatest surprises in science. In a room filled with flashing detectors and falling particles, a new vision of the atom was born, one that would change our understanding of matter forever. And to think it all came from something as gentle as a flicker on a screen, and a scientist bold enough to ask, why did that bounce? By the early 1930s, the atom was beginning to resemble a rather crowded cocktail party. We had electrons zipping around in orbits, a tiny but hefty nucleus sitting in the center, and inside that nucleus, positively charged protons rubbing shoulders and pretending they got along. And yet something still didn't quite add up. Physicists had been puzzling over the atomic nucleus for years. If protons carried positive charge, and if like charges repel each other, then what on earth was holding them together in such close quarters? It was like trying to stack a bunch of magnets all facing the same way and expecting them to stay put. Nature didn't seem to mind, but physicists did. And then there was the mystery of atomic mass. When scientists tallied up the mass of an atom based on the number of protons and electrons, the numbers never quite matched what they measured experimentally. There was always a little extra weight. Not just a huge amount, but enough to raise an eyebrow. Clearly, something was hiding in the nucleus. Something with mass but no charge. Something that could add heft without adding a push or a pull. Entered James Chadwick, a quiet and determined British physicist who looked less like a particle smasher and more like someone who might help you find a good book in a quiet library. But make no mistake, Chadwick was on the hunt for a ghost. For years, physicists had speculated that a neutral particle might exist, but proving it had proven elusive. In 1932, Chadwick finally caught it. The breakthrough came when he revisited a puzzling experiment by Frederick and Irene Joly-Curie, who had bombarded beryllium with alpha particles and noticed that it emitted an unusual but highly penetrating radiation. They assumed it was gamma rays, very high-energy electromagnetic waves. But the energy levels seemed oddly high, too high, almost suspiciously so. Chadwick suspected something else entirely. What if this wasn't electromagnetic radiation, but a stream of actual particles? Particles that had no electric charge and yet had enough mass to knock other atoms around. He tested the idea by letting the mysterious radiation hit various targets like hydrogen and nitrogen and measuring the recoil. Based on the results, it became clear. This radiation consisted of particles about the same mass as protons, but with no charge. He had found the neutron. It may not have had the theatrical sparkle of discovering the electron or the dramatic surprise of the gold foil experiment, but the neutron turned out to be absolutely essential. It completed the picture of the atom's nucleus. Now it made sense why the mass of atoms was often more than the number of protons alone could explain. Those extra particles weren't hiding, they were simply neutral. With the neutron added to the mix, the atom's nucleus became a more comfortable, albeit busier place. Protons still repelled each other with their positive charges, but neutrons acted as a kind of nuclear buffer. They added mass and stability, helping to glue the nucleus together through what we now call the strong nuclear force. It's one of the four fundamental forces of nature, and it's the one that's responsible for keeping the atomic nucleus from flying apart in a flurry of electrostatic anxiety. The neutron was also key to understanding isotopes. Chemists had long known that some atoms of the same element could behave identically in chemical reactions, but have different masses. These were called isotopes, and now we knew why. They had the same number of protons. That's what made them the same element, but different numbers of neutrons, giving them different atomic masses. For example, carbon usually has 6 protons and 6 neutrons, carbon 12. But there's also carbon 13 with an extra neutron, and carbon 14, which is radioactive and famously used in dating ancient artifacts. Thanks to neutrons, atoms came with variations. Same element, different flavor. Chadwick's discovery also opened the door to a new era of nuclear physics. Neutrons, unlike protons or electrons, could penetrate atomic nuclei without being repelled or deflected by electric charge. That made them ideal tools for poking and prodding atoms, splitting nuclei, and initiating chain reactions. In fact, the neutron would soon become the star player in nuclear fission. When scientists later bombarded heavy elements like uranium with slow-moving neutrons, the atoms didn't just absorb them, they broke apart. And when they did, they released enormous amounts of energy along with more neutrons to keep the reaction going. This chain reaction would lead to both nuclear power and nuclear weapons, for better or for worse. But at the core of it all was the humble neutron, silently slipping into nuclei and turning matter into energy. As discoveries go, the neutron is almost an anti-celebrity. It doesn't sparkle like the electron or shout like the proton. It doesn't carry charge. It never shows up in electric currents. It just sits there, solid and stoic, adding weight and binding protons like a patient sibling holding hands at the dinner table to stop a food fight. Yet, despite its quiet nature, the neutron plays a vital role in everything from atomic stability to stellar physics. In the hearts of stars, where atoms are fused under immense pressure, neutrons are constantly being shuffled and exchanged. In neutron stars, those ultra-dense remnants of collapsed supernovae, matter is compressed into a sea of neutrons so tightly packed that a single teaspoon would outweigh a mountain. Chadwick, for his part, didn't bask in celebrity. He was awarded the Nobel Prize in Physics in 1935, and he continued his work during a turbulent time in history. During the Second World War, he became involved in the British atomic bomb project and later joined the Manhattan Project in the United States. Though a reserved man, he understood the significance of his work and the dual-edged sword it represented. The neutron may have arrived later to the atomic party, but it changed everything. It made the nucleus complete. It made isotopes understandable. It made nuclear reactions controllable, or sometimes uncontrollable. Without it, atoms wouldn't stick together properly. Nuclear reactors wouldn't function, and carbon dating wouldn't tell us how old ancient bones are. Even our understanding of particle physics and quantum mechanics would be incomplete without accounting for the neutron's subtle mass and its participation in fundamental forces. It's funny how much can depend on something that doesn't even have a charge. In the end, the discovery of the neutron added the final major puzzle piece to the classic image of the atom: electrons buzzing around a dense nucleus made of protons and neutrons. It gave structure and symmetry to our understanding of matter, and it laid the groundwork for decades of new questions. Because in science, every answer tends to generate at least 3 new questions. And while the neutron answered the mystery of atomic mass and nuclear cohesion, it also hinted at deeper layers yet to come. What held the protons and neutrons together? What were neutrons made of? Could they be split further? The journey inward was far from over. But for that moment, in the early glow of Chadwick's careful measurements, the atom finally felt, if not complete, then at least a little less mysterious. With the neutron in place, the atomic family finally had its quiet middle child. No flash, no fuss, just weight, balance, and the glue that holds the heart of matter together. At first glance, light seems like the most familiar thing in the universe. We wake up with it, we read by it, we bask in it, and we flick switches expecting it to appear on command. Light is comfort, clarity, sunrise, and science fair. But the more scientists tried to understand light, not just use it, but understand it, the stranger it became. By the turn of the 20th century, light was starting to act in ways that no one could quite explain. It flickered between two identities, sometimes a wave, sometimes a particle, sometimes both, sometimes neither. Like a magician who never reveals the trick, light refused to play by the old rules. Back in the 19th century, most physicists were pretty confident about what light was. Thanks to the work of James Clerk Maxwell and others, light was understood as a wave, an electromagnetic wave to be precise. It could be reflected, refracted, and diffracted. It had wavelength and frequency. It traveled through space like ripples through water, except it didn't need a medium. Waves were smooth, continuous, and reliable. Everything was great, until it wasn't. Enter Max Planck, a German physicist who was about as skeptical of revolutionary science as you could get. He was calm, methodical, and very fond of classical physics. But in the late 1800s, he found himself tangled into a very non-classical problem, the ultraviolet catastrophe. This was the unsettling prediction that, according to classical theory, a black body, an idealized object that absorbs and emits all frequencies of radiation, should emit infinite energy at ultraviolet and higher frequencies. In other words, if the math were right, every warm object in the universe should be blasting us with deadly rays all the time. Spoiler, this was not happening. Planck didn't set out to overhaul physics, he just wanted the math to work. In a move he described as an act of desperation, he made a peculiar assumption. What if light energy wasn't emitted in a smooth, continuous stream? What if it came in discrete packets, little bundles he called quanta? He introduced a new constant, now known as Planck's constant, to describe the size of these energy bundles. According to his formula, the energy of each quantum is proportional to the frequency of the light. Higher frequency, higher energy; lower frequency, lower energy. Suddenly, the math lined up perfectly with experimental results. The ultraviolet catastrophe was avoided. Everyone exhaled, except Planck wasn't entirely sure what he'd just done. He didn't know if quanta were real or just a mathematical trick. But then came a young patent clerk with a fondness for trains and thought experiments, Albert Einstein. Yes, that Einstein. He took Planck's idea and ran with it. In 1905, he proposed something radical. Light doesn't just act like it's made of particles, it is made of particles. He called these particles light quanta, though we now know them as photons. Tiny, indivisible packets of light energy traveling through space not as a smooth wave, but as discrete pulses. Einstein wasn't just speculating for fun, he was trying to solve another physics puzzle, the photoelectric effect. This is what happens when light shines on certain metals and causes them to release electrons. According to the wave theory of light, increasing the brightness should eventually knock electrons loose no matter the color. But that's not what scientists observed. Instead, low-frequency light, no matter how intense, failed to eject any electrons. Meanwhile, high-frequency light, even if dim, did the trick immediately. Einstein's photon theory explained it beautifully. Each photon carries a specific amount of energy, and only photons with enough energy can liberate an electron. Brightness didn't matter. Frequency did. For this elegant solution, Einstein was awarded the Nobel Prize in Physics. Not for relativity, mind you, but for figuring out that light, the wave, was also a particle, or at least something that behaved like one. With Planck and Einstein leading the way, physicists were forced to accept a strange new reality. Energy was quantized, light came in packets, the universe at its most fundamental level had a grainy texture. The dream of a smooth, continuous world was beginning to crumble. But things only got weirder from there. As experiments grew more precise, light continued to confound expectations. It still produced interference patterns, a hallmark of waves. Shine light through two slits, and you still get the familiar bands of brightness and darkness that suggest overlapping wavefronts. But send photons through those slits one at a time, and you still get interference. It's as if each photon is interfering with itself, as though it travels through both slits at once, like a ghost unsure of its path. This behavior gave rise to one of the most baffling concepts in modern physics: wave-particle duality. Light, and later electrons and other particles, seem to exist in a strange limbo, sometimes acting like particles, sometimes like waves, and never committing fully to either until someone was watching. Not metaphorically watching, but measuring. Observation, it turned out, changed everything.
This duality wasn't just philosophical, it was demonstrable and deeply unsettling. In a universe governed by classical laws, particles and waves are distinct entities. But quantum theory tossed that clean division out the window. Suddenly, particles could spread out like waves. Waves could collapse into particles. Certainty was replaced with probability. The universe no longer ticked like a predictable clock. It shimmered with ambiguity. Even light speed became part of the enigma. It always travels at the same speed in a vacuum, about 299,792 kilometers per second, no matter your frame of reference. This constancy, which underpins Einstein's theory of relativity, is beautiful but bizarre. It means that the faster you move, the more space and time bend to keep the speed of light unchanged. The more you learn about light, the more it seems to be nature's ultimate shapeshifter. And all of this, the photons, the quanta, the duality, emerged from experiments with glowing filaments, shining metals, and radiation that didn't quite behave. The tiniest nudges in experimental results cracked open the door to a deeper reality, one where the classical rules no longer applied. Physicists weren't just discovering new facts, they were uncovering a new framework. Quantum theory was still in its early days, but the implications were already staggering. It wasn't just light that behaved this way. Electrons, protons, entire atoms, all were found to follow the same fuzzy logic. The universe at its smallest scale was built on uncertainties, probabilities, and strange patterns that defied classical intuition. But it all began with light, with the glow of heated metals, the flicker of photons, and the peculiar realization that the most familiar thing in the world might also be the strangest. Light, once thought to be a simple wave, turned out to be a quantum creature, both wave and particle, neither fully one nor the other, depending on how you asked. And in embracing that weirdness, physics found a new language, one that would go on to explain everything from atomic structure to the birth of stars to the nature of information itself. All because light decided it didn't want to be just one thing. It wanted to be both. In the early decades of the 20th century, the atom had become a rather confusing place. Electrons had been discovered, the nucleus had been mapped out, and thanks to Rutherford's gold foil experiment, we knew the atom was mostly empty space. But no one could quite explain how everything fit together. Classical physics insisted that electrons orbiting a nucleus should spiral inward and crash, like doomed satellites. And yet, atoms miraculously stayed whole. The universe, thankfully, was not spontaneously collapsing into itself. That was the puzzle facing a young Danish physicist named Niels Bohr. He had a soft-spoken manner, a gentle wit, and a mind that delighted in paradoxes. Bohr was the kind of person who could ponder contradictions over coffee and then calmly rewrite the rules of atomic structure between sips. While working with Rutherford in Manchester, Bohr became obsessed with one particularly mysterious clue: the strange and beautiful patterns of light given off by atoms. If you pass an electric current through hydrogen gas, for instance,
It doesn't glow with a smooth rainbow of colors. Instead, it emits light at very specific wavelengths, distinct lines of red, blue-green, and violet. These aren't smudges, they're razor-sharp frequencies, like musical notes played by an invisible instrument. Each element has its own unique spectral fingerprint, a barcode of light that tells you exactly what kind of atom you're looking at. This phenomenon had been known for decades, but no one could explain why it happened. Why would atoms, when excited, emit only certain colors and not others? What was determining the structure of this atomic song? Bohr had an idea, one that would blend classical mechanics, new quantum ideas, and a dash of creative audacity. He proposed that electrons didn't orbit the nucleus at just any distance. Instead, they occupied specific energy levels, what he called quantized orbits. Only certain orbits were allowed, like the rungs on a ladder. An electron couldn't just hover between them. It could jump from one level to another, sure, but only by absorbing or emitting a specific amount of energy, usually in the form of light. If this sounds familiar, it's because Bohr was taking a cue from Planck and Einstein's quantum work. Just as light came in packets, Bohr suggested that an electron's energy did too. Each orbit corresponded to a specific energy level. When an electron dropped from a higher orbit to a lower one, it released a photon with energy equal to the difference between those levels. That photon had a very specific frequency, hence the sharp spectral lines. Bohr's model made a stunning prediction, the exact wavelengths of hydrogen's spectral lines. Using his equations, he calculated the frequencies of the emitted light, and they matched the experimental data perfectly. The theory didn't just explain what was happening, it predicted it. Suddenly, the atomic spectrum wasn't a mystery, it was a roadmap. Bohr's model brought order and logic to a realm that had been stubbornly weird. The atom wasn't a random jumble of parts. It had structure, rhythm, and hierarchy. Electrons weren't whizzing around chaotically, they were dancing in defined patterns, leaping between levels like acrobats. There was a certain elegance to the whole thing, a symmetry that physicists found deeply satisfying. Bohr had taken the unruly quantum behavior of particles and turned it into a model that could be visualized, calculated, and taught. His atom looked like a tiny solar system, with electrons orbiting a nucleus much like planets around the sun, except with hard boundaries and sudden jumps.
Of course, there were caveats. Bohr's model worked beautifully for hydrogen, the simplest atom with only one electron, but began to fall apart with more complex atoms. It couldn't fully explain why electrons didn't radiate energy while orbiting or why their paths didn't slowly decay. And it didn't incorporate the full weirdness of quantum mechanics, like wave-particle duality or Heisenberg's uncertainty principle. But at the time, it was a massive leap forward. Bohr's model gave physicists a bridge between classical intuition and quantum reality. It wasn't the final answer, but it was a functional map, a guide through the haze. It showed that energy in atoms was quantized, not continuous. It explained spectral lines, and it hinted at the deeper structure of matter, where motion and energy weren't just analog values, but came in steps. And let's be honest, it was also just incredibly satisfying. There's something deeply appealing about electrons zipping around in clean orbits, dropping photons like breadcrumbs as they descend. It turned the chaotic image of the atom into something almost musical, with discrete notes and harmonic rules. Bohr's contribution didn't stop with the atom. He would go on to be a towering figure in the development of quantum theory, helping lay the philosophical groundwork for how scientists interpret the bizarre behavior of the subatomic world. He was a mentor to many, including Heisenberg, and often found himself at the center of debates about what quantum mechanics really meant. One of Bohr's most famous sayings is, "Anyone who is not shocked by quantum theory has not understood it." He believed in the strange, not as an exception, but as a foundation. And yet, his own model, the neat planetary atom, was perhaps his most grounded and intuitive contribution. It gave people a way to see the invisible. It's also a reminder that in science, progress often comes in layers. Each model brings us closer to the truth, but none is the final word. Bohr's atom would eventually be refined and replaced by more accurate quantum mechanical models, where electrons aren't points in orbit, but clouds of probability. Still, the Bohr model remains a crucial milestone, a moment when imagination, mathematics, and experiment lined up just long enough to illuminate the atom's inner architecture. It's fitting that light played such a central role in this story. Bohr used light to understand atoms, and atoms, in turn, use light to speak their secrets. Every spectral line is a whisper from an electron, telling us where it has been and what it left behind. And thanks to Bohr, we know how to listen. In classrooms around the world, students still draw Bohr's atom, circles for orbits, dots for electrons, knowing that it's a simplified picture, but a powerful one. Because sometimes, even in the complex landscape of quantum physics, a simple sketch can point the way to a deeper truth. And sometimes, the universe really does behave like a planetarium full of particles, leaping through space and singing in light. By the mid-1920s, physicists were starting to feel a bit seasick. The classical world of predictable laws and tidy trajectories was steadily being replaced by something far stranger. Atoms were no longer miniature solar systems with electrons neatly orbiting their nuclei. Instead, the deeper scientists looked, the more it seemed that reality itself was fuzzy, fluid, and oddly non-committal. Enter Werner Heisenberg, a brilliant young German physicist with a sharp mind and a healthy skepticism for things that couldn't be measured. He was the kind of person who found comfort in equations, not metaphors, and preferred mathematical clarity over philosophical hand-waving. But even Heisenberg, the logical pragmatist, would soon find himself confronting one of the strangest and most unsettling truths in modern physics. Heisenberg was trying to understand the behavior of electrons, not just where they were, but how they moved. Classical physics told him that, in principle, you could know both an object's position and its velocity with perfect precision. After all, that's how we navigate the world. If you know where a car is and how fast it's going, you can predict where it will be a few seconds later. Easy. But atoms, as it turned out, weren't interested in being easy. As Heisenberg worked through the math of quantum mechanics, he realized something astonishing. The more precisely you tried to measure an electron's position, the less precisely you could know its momentum, its speed and direction, and vice versa. This wasn't due to faulty instruments or human error. It was a fundamental property of nature. Heisenberg's uncertainty principle was born. Formally, it states that the product of the uncertainty in position and the uncertainty in momentum is always greater than or equal to a very small number, Planck's constant divided by 4 pi. In plain English, you cannot know both where a particle is and how fast it's going with perfect accuracy at the same time. The universe won't let you. This wasn't just weird, it was revolutionary. It meant that the behavior of particles at the quantum level couldn't be described with classical certainty. You couldn't draw a neat little diagram of an electron zipping around a nucleus. Instead, you had to talk in terms of probabilities, likelihoods of finding an electron somewhere within a cloud of possibilities. In a way, it was like trying to track a buzzing mosquito in a dark room with a flashlight. The moment you shine the light to see where it is, you've already disturbed it. Your act of observing changes its behavior. The better your flashlight, the more disruptive your search becomes. For Heisenberg, this wasn't just a quirky footnote, it was a fundamental shift in how we think about reality. Classical mechanics had taught us that the universe was like a clock, Complex, yes, but ultimately predictable. Quantum mechanics said no. The universe was more like a jazz performance, structured but improvisational, governed by rules but always dancing around uncertainty.
Some physicists found this deeply unsettling. Einstein famously wasn't a fan. God does not play dice with the universe, he declared. He couldn't accept a theory that seemed to abandon cause and effect in favor of probabilities. But Heisenberg and others held their ground. It wasn't about God playing dice. It was about acknowledging that nature, at its core, plays by rules we're still learning to understand. And in this new world of uncertainty, measurement itself became a delicate art. To study atoms, you couldn't just poke them and see what happened. You had to use inference, mathematics, and a healthy respect for the fact that your tools were part of the system. The observer was no longer separate from the observed. This idea gave rise to a new kind of physics, one where wave functions described particles not as objects in space, but as clouds of probability. An electron wasn't here or there, it was likely to be in one place, less likely to be in another, and virtually impossible to pin down with absolute certainty. Only when you made a measurement, when you actually looked, did the wave function collapse and reveal a single outcome. And even then, that outcome is just one possibility among many. It's a bit like flipping a coin and only finding out whether it landed heads or tails once you lift the cup. Until that moment, it exists in a kind of superposition, not both, not neither, but something stranger. Heisenberg's principle didn't just apply to electrons, it applied to everything. In theory, it applies to you, me, your coffee cup, and your socks. It's just that for big objects, the uncertainties are too small to notice. You can know both the position and speed of a baseball pretty accurately. But for tiny particles, electrons, photons, and their subatomic friends, the uncertainties dominate. This realization didn't break physics, it expanded it. It forced scientists to think differently, to abandon the old metaphors and embrace the math. It gave rise to quantum mechanics, a theory that would go on to explain semiconductors, lasers, superconductors, and more. It opened the door to quantum computing, where particles can hold multiple states at once, and to quantum encryption, where information can be fundamentally protected by the laws of physics. But perhaps more than anything, Heisenberg's uncertainty principle taught us humility. It reminded us that even the most precise instruments and the most brilliant minds have limits, not because we're not clever enough, but because the universe is built that way. At the smallest scales, reality isn't about knowing, it's about predicting probabilities and accepting the dance of chance. And yet, from that uncertainty comes structure. Atoms form stable configurations. Molecules behave predictably. Stars burn with reliable light. Somehow, out of this quantum blur emerges the solidity of the world we live in. It's a paradox that still stirs the minds of physicists, that certainty, order, and beauty can arise from a foundation that is fundamentally uncertain. Heisenberg himself understood this deeply. He didn't see the uncertainty principle as a flaw, but as a revelation. It didn't make nature less real. It made it more alive. The atom was no longer a simple machine. It was a dynamic, ever-shifting expression of probability, energy, and possibility. And with that insight, the way we measured atoms and thought about them changed forever. From sharp lines to soft clouds, from precision to probability, the journey into the atom had taken us to a place where being unsure wasn't a weakness, but a new kind of understanding, a recognition that even in the deepest parts of matter, a little uncertainty can go a very long way. In the misty world of quantum mechanics, where particles behave like waves and certainty slips through your fingers like smoke, came a man with a head full of equations and an idea that involved a very unfortunate cat.
His name was Erwin Schrödinger, and he was about to give quantum physics one of its most iconic images and one of its most powerful mathematical tools. Let's start with the equation. Schrödinger's equation is, to put it simply, the heart of quantum mechanics. It does for subatomic particles what Newton's laws did for falling apples and swinging pendulums. It tells you how a quantum system evolves over time, how its state changes, how its energy behaves, and how its probabilities shift. But instead of tracking the motion of solid objects, it describes something much more subtle: the wave function. The wave function is not a wave in the traditional splashy surf sense. You can't surf on it or see it ripple across a pond. It's a mathematical expression that encodes everything we can possibly know about a quantum system: where a particle might be, how fast it might be moving, what energy it might have. All of these are wrapped up in a single complex value function. It's like a map, but one made entirely of potential outcomes. When you square the wave function, you get a probability distribution, a sort of heat map of where the particle is likely to be found. This is not because the particle is hiding somewhere and we just don't know where. According to the quantum worldview, it genuinely does not have a definite position until it's measured. Until that moment, it exists in a superposition, a smeared out state of possibilities. Schrödinger wasn't just trying to come up with abstract math. He wanted a visual, intuitive way to understand how particles behaved at the quantum level. Building on the ideas of de Broglie, who had suggested that particles could behave like waves, Schrödinger proposed that if electrons had wave-like properties, perhaps their behavior could be modeled using a wave equation. That wave would represent the electron's probability cloud, not its physical path. He formulated his equation in 1926, and it quickly became one of the cornerstones of modern physics. With it, scientists could predict the allowed energy levels of electrons in atoms, the shapes of atomic orbitals, and the behavior of subatomic particles with startling accuracy. The Bohr model of the atom had shown where electrons could be. Schrödinger's model showed why they were there and how they moved within their allowed energy levels. Instead of neat planetary orbits, the electron became a fog of probability, hovering in shell-like regions around the nucleus. Each orbital wasn't a path, it was a zone of likelihood. And this wasn't just a clever metaphor. These shapes could be calculated, visualized, and tested against experimental data. The quantum cloud was real, even as it was invisible. But quantum mechanics never likes to leave things too tidy. As Schrödinger worked with his wave function, he began to wrestle with a growing discomfort. While his equation worked brilliantly, its implications were strange, even disturbing. According to the prevailing interpretation at the time, the wave function doesn't just describe potential outcomes, it is the system, right up until a measurement is made. Measurement collapses the wave function into a single outcome. Before that, the system exists in a liminal state of overlapping possibilities. This is where Schrödinger's cat entered the story. In an effort to highlight what he saw as a paradox, or perhaps even a flaw in the prevailing view, Schrödinger proposed a now famous thought experiment. Imagine placing a cat in a sealed box. Inside the box is a vial of poison, a tiny bit of radioactive material, and a Geiger counter. If the radioactive atom decays, the Geiger counter detects it and breaks the vial, releasing the poison and ending the cat's career in one rather dramatic moment. If the atom does not decay, the cat stays alive. Now here's the twist. Radioactive decay is a quantum event. It's governed by probability. According to quantum mechanics, until someone opens the box and checks, the atom exists in a superposition of decayed and not decayed. And if the atom is in superposition, so is the mechanism, the poison vial, and yes, the cat. That means, in theory, the cat is both alive and dead at the same time. Not in a ghostly way, but in a real physical superposition. Only when someone observes the system by opening the box does the wave function collapse into one outcome or the other. Schrödinger didn't propose this to support the theory, he was horrified by it. He intended the cat scenario to be absurd, a kind of wake-up call to show just how weird and troubling the implications of quantum theory could be when extended to everyday objects. After all, nobody actually sees half-alive, half-dead cats wandering around. Reality seems to choose an outcome even when nobody's looking. But instead of killing the theory, Schrödinger's cat became its mascot. Physicists embraced the paradox, debated it, and built entire schools of interpretation around it. Some believe that observation really does collapse the wave function. Others propose that all outcomes actually happen, just in separate branching universes. In one world, the cat lives, in another, it doesn't. This became the foundation of the many worlds interpretation. Still others tried to build more deterministic models or hidden variable theories in an attempt to restore a sense of classical order. But no matter the interpretation, the math stayed the same. Schrödinger's equation continued to work, guiding quantum mechanics through decades of breakthroughs, inventions, and philosophical debates. It's worth noting that Schrödinger himself wasn't just a one-hit wonder. He contributed to a wide range of topics in physics and biology, and he remained a thoughtful, sometimes restless voice in scientific philosophy. His cat may have become the most famous quantum feline in history, but his wave equation was the true legacy. It gave scientists a powerful tool to predict how particles behave, how atoms form bonds, and how matter holds itself together. At its heart, Schrödinger's work revealed that particles, like electrons, are not dots moving along a line, but clouds of possibility. They can interfere with themselves, tunnel through barriers, and defy the logic of classical motion. They are not here or there, they are somewhere in a statistical sense, until we ask the question directly. And once we ask, the universe answers, but only with one outcome. In the quantum world, reality is not fixed in advance. It unfolds moment by moment, shaped by interaction, observation, and chance. Schrödinger's wave function didn't just describe atoms, it rewrote our understanding of what it means to exist. So whether you picture the atom as a cloud, a blur, a probability field, or a purring feline in a box of quantum doom, know this. The world beneath the surface is richer, stranger, and far more delicate than it appears. And every time we open a box, literal or mathematical, we're not just observing the universe, we're participating in its unfolding. By the time physicists had gotten comfortable with electrons as clouds of probability and cats as thought experiments, the atom was already whispering a new secret. There were still more layers hiding beneath the surface. The once simple building blocks of matter, once thought to be indivisible, had become dense hubs of complexity. It was like discovering that your neatly arranged desk drawer actually contained another drawer inside it, and inside that, a whole colony of mysterious gadgets chatting in code. The story of the atom was evolving again. Quantum mechanics had explained a great deal, and Schrödinger's wave functions were doing an excellent job at describing how electrons behaved in atoms, but the forces that held the atomic nucleus together, those were still a little opaque. Protons, after all, are all positively charged. According to the laws of electromagnetism, they should repel one another violently. It would be like trying to keep a pile of north-pointing magnets crammed into a tiny space. Nature doesn't usually allow that kind of party. And yet, there they were, snuggled together in the nucleus, not flying apart. Clearly, there had to be something else at play, some stronger glue, some force more powerful than the electromagnetic one. Enter the strong nuclear force. It's the mightiest of the four fundamental forces of nature, but also the most elusive. Unlike gravity or electromagnetism, which act over long distances, the strong force only works at incredibly short ranges, about the width of a proton. But within that minuscule range, it dominates. It binds protons and neutrons together in the nucleus and refuses to let them drift apart. To understand how this force operates, physicists needed a new framework, one that went beyond particles as points and imagined them instead as ripples in underlying fields. This was the birth of quantum field theory. Quantum field theory, or QFT for short, is where things really start to feel like a blend of physics and poetry. Instead of treating particles as tiny objects that move through space, QFT says that every type of particle is actually an excitation, a little ripple or vibration in a field that fills all of space. Electrons are ripples in the electron field, photons are ripples in the electromagnetic field. Everything is fields all the way down. This shift in perspective wasn't just a philosophical tweak. It changed how physicists calculated interactions. Fields can create and annihilate particles. They can overlap and interfere. And within this field-based reality, strange new possibilities emerged. Particles that appear and vanish, momentarily borrowed from the vacuum itself. These are known as virtual particles, and they play a crucial role in how forces are transmitted. Imagine two particles interacting, say two electrons repelling each other. In QFT, this isn't because they directly push on each other like billiard balls. Instead, one electron emits a virtual photon, a messenger particle that zips over to the other electron, delivering the message, "Hey, scoot." The photon is virtual because it exists for a brief moment, just long enough to mediate the force and then disappears. The same logic applies to the strong force, except instead of photons, the messengers are called gluons. Yes, gluons. The name is delightfully literal. Gluons are the particles that carry the strong force, binding quarks together inside protons and neutrons. And yes, quarks. Because it turns out that even protons and neutrons, those supposedly elementary particles, aren't elementary at all. They're made of even smaller particles.
Each proton or neutron is composed of three quarks, held together by the relentless grip of gluons. These quarks come in flavors: up, down, strange, charm, top, and bottom. And for some reason known only to the whimsical minds of physicists, these are the official terms. A proton contains two up quarks and one down quark. A neutron has one up and two down quarks. The gluons that bind them don't just stick them together like cosmic glue, they also constantly swap between the quarks, changing their color charge, a quantum property that has nothing to do with actual colors, but helps keep track of how the strong interaction behaves. The result is a chaotic, jittery ballet of particles exchanging force-carrying messengers at blistering speed, all confined within a space smaller than a single atom. The sheer strength of the strong force is staggering. It's about 100 times stronger than the electromagnetic force and 10,000 times stronger than the weak nuclear force. But it's picky. Outside the atomic nucleus, its influence drops off to nearly zero. It's like a bodybuilder who refuses to lift anything outside his own kitchen. But the strong force isn't the only game in town. Alongside it, physicists discovered a whole zoo of particles: muons, pions, kaons, neutrinos, and more. Some were stable, many were fleeting, and all were pieces of the same quantum puzzle. This expanding collection became known as the particle zoo, and for a while it was more chaotic than enlightening. It was as if nature had opened her handbag and dumped out a tangled collection of subatomic receipts, keys, and loose change. The breakthrough came with the development of the Standard Model, a theoretical framework that organized these particles into categories and explained how they interacted. According to the Standard Model, all matter is made of a small set of fundamental particles: quarks, leptons, like the electron, and force carriers, like photons and gluons. Everything else, atoms, molecules, cats, galaxies, is just combinations of these tiny bits. It's hard to overstate how successful the Standard Model has been. It explains nearly all known particle interactions with incredible precision. It predicted the existence of particles long before they were discovered, and in 2012, it was crowned with the discovery of the Higgs boson,
the particle associated with the Higgs field, which gives mass to other particles. But even with its successes, the Standard Model isn't the final story. It doesn't explain gravity. It doesn't tell us why the fundamental constants have the values they do. It doesn't account for dark matter or dark energy, which seem to make up most of the universe. In many ways, it's a map of familiar territory with big question marks just beyond the edges. Still, what the Standard Model and quantum field theory have taught us is nothing short of astonishing. That particles are just ripples in fields, that forces are carried by particles flickering in and out of existence, that protons, once thought indivisible, are seething bundles of smaller entities held together by the strongest force known to science. Atoms, it turns out, are not simple at all. They are symphonies of fields, dances of probabilities, and collisions of energy and structure. They are galaxies of motion in miniature, held together not by static bonds, but by constant humming activity. Even in the calmest piece of matter, say the end of your nose, there are trillions upon trillions of gluons flitting between quarks, virtual particles bubbling in and out of reality, and fields humming beneath it all. What began as a search for the smallest pieces has led to a layered, dynamic universe. A universe where the deeper you look, the less things look like things and more like interactions, energies, and patterns that never quite sit still. The zoo is strange. The forces are hidden. The fields are everywhere. And yet, from all this invisible chaos comes the tangible world: tables, trees, stars, you. A universe built from whispers and wiggles, held together by rules we are only just beginning to understand. By the early 20th century, scientists had taken the atom apart in theory, teased out its pieces with equations, and mapped out the strange forces that held it all together. But there was still one thing they hadn't done: crack the atom open and see what came flying out. That would soon change. It turns out that atoms, those tiny bundles of organized chaos, are also stores of extraordinary energy. Not energy in the warm and cozy, light a candle sort of way, but energy capable of reshaping landscapes, lighting cities, or leveling them. Nuclear physics would bring about some of humanity's greatest advances and its darkest moments, all thanks to what happens when you split or fuse the very heart of matter. Let's start with the split: nuclear fission. Fission is what happens when the nucleus of an atom, typically a heavy one like uranium or plutonium, becomes unstable and breaks apart into smaller nuclei. When this happens, a tremendous amount of energy is released, along with a few loose neutrons. These neutrons can then strike other atoms, causing more fission, releasing more energy and more neutrons in turn. This chain reaction can unfold in the blink of an eye or be carefully controlled. The key here is that the mass of the resulting particles after fission is slightly less than the mass of the original atom. That lost mass hasn't vanished. It's been converted into energy, as predicted by Einstein's famous equation E equals mc squared. Since c, the speed of light, is a very large number, even a tiny amount of mass can produce a staggering amount of energy. The first experimental demonstration of fission came in 1938 when German scientists Otto Hahn and Fritz Strassmann bombarded uranium with neutrons and noticed unexpected byproducts. Physicists Lisa Meitner and Otto Frisch quickly realized that the uranium nucleus was splitting, fissioning, into smaller elements, and they calculated the massive energy released in the process. It was a groundbreaking moment. They hadn't just discovered a new kind of reaction, they'd stumbled upon a new kind of power. Suddenly, the atom was no longer just a conceptual playground for theorists. It was a battery, a grenade, a sun in miniature. As the Second World War loomed, the implications of fission were obvious and terrifying. If you could build a device that triggered a sustained chain reaction, you could unleash unimaginable destruction. That race led to the Manhattan Project, a secret Allied effort to build an atomic bomb before Nazi Germany could. It brought together some of the greatest minds in science, including Oppenheimer, Fermi, Szilard, and many others, working in remote laboratories under intense secrecy. In 1945, the world saw the results. Two bombs, nicknamed Little Boy and Fat Man, were dropped on the Japanese cities of Hiroshima and Nagasaki. They killed over 100,000 people instantly, with many more dying in the aftermath. Entire neighborhoods were flattened in seconds, their energy released not from fire or gas, but from the splitting of atoms. It was power on a scale that humanity had never known before, and a warning etched in ash and silence. The use of atomic bombs brought an end to the war, but also a deep moral and philosophical reckoning. What had once been a symbol of pure scientific curiosity, the quest to understand the atom, had become a weapon of mass destruction. The paradox of nuclear physics was born. The same discoveries that offered limitless energy also threatened total annihilation. But even in the shadow of destruction, the pursuit of nuclear knowledge continued. Scientists and engineers turned their attention to peaceful applications of fission, particularly in generating electricity. In a nuclear power plant, the chain reaction is carefully controlled using moderators and control rods that absorb excess neutrons. Instead of releasing the energy all at once, as in a bomb, the process is slowed to a steady simmer. The heat produced by fission boils water, which turns turbines, which generates electricity. Clean, efficient, and carbon-free, at least in terms of emissions.
Of course, it's not without its downsides. Nuclear power plants produce radioactive waste that remains hazardous for thousands of years. Accidents, though rare, can be catastrophic, as seen in Chernobyl and Fukushima. And the line between civilian and military nuclear technology is razor thin. Still, for all its risks, nuclear power remains one of the most efficient ways to produce large amounts of electricity without burning fossil fuels. But fission is only half the nuclear story. Let's not talk about fusion, the process that powers the sun. Fusion is the opposite of fission. Instead of splitting heavy atoms apart, fusion involves forcing light atoms, like hydrogen, to combine into heavier ones, such as helium. This process also releases energy, and a lot of it. Fusion is what makes stars shine. In the sun's core, under intense heat and pressure, hydrogen nuclei collide and fuse, releasing the energy that bathes our planet in light and warmth. Scientists have long dreamed of replicating this process on Earth, and for good reason. Fusion fuel is abundant. Hydrogen is everywhere. It produces no long-lived radioactive waste. And unlike fission, there's no chain reaction runaway effect. Fusion is self-limiting. If something goes wrong, it simply stops. But there's a catch, a big one. Fusion requires temperatures of over 100 million degrees Celsius, hotter than the core of the sun. Containing something that hot is, well, tricky. You can't build a container out of metal or ceramic. Everything would melt. Instead, scientists use magnetic fields to suspend the hot plasma in midair inside devices called tokamaks and stellarators. These look like enormous futuristic donuts, humming with magnetic force and scientific ambition. Despite decades of effort, controlled fusion for power generation has remained tantalizingly out of reach. We've achieved fusion in the lab, short bursts, experimental pulses, but not yet in a way that produces more energy than it consumes. Still, progress continues, and international projects like ITER in France aim to crack the challenge in the coming decades. We have, however, achieved fusion in a more dramatic form, the hydrogen bomb. Unlike an atomic bomb, which uses fission, a hydrogen bomb uses a fission reaction to trigger a fusion reaction. The result is an explosion hundreds or even thousands times more powerful than the bombs dropped on Japan. It's fusion weaponized. And it's why the Cold War was so terrifying, because once both superpowers had hydrogen bombs, mutual destruction became a very real possibility.
And yet, nestled within all this danger is incredible promise. Nuclear physics has revolutionized medicine. Radioisotopes are used in imaging, diagnostics, and cancer treatment. Tracers help track chemical pathways in the body. Radiation therapy targets tumors with pinpoint precision. The very forces that can destroy cities are also saving lives in hospitals around the world. In geology and archaeology, radiometric dating allows us to measure the ages of rocks, fossils, and ancient artifacts with astonishing accuracy. In industry, radiation is used to sterilize equipment, scan welds, and improve crop varieties. The benefits ripple far beyond power plants and physics labs. Still, the paradox remains. Nuclear physics is a field of astonishing elegance and terrifying potential. It reveals the universe's deepest secrets and reminds us that knowledge is never neutral. With each breakthrough, we are faced with choices: how to use what we've learned, and whether our wisdom can keep pace with our power. We split atoms to understand the world, and in doing so, gave ourselves the power to destroy it or to sustain it, depending on which direction we choose. Nuclear physics asks hard questions, not just about nature, but about ourselves. What kind of species splits the atom and wonders what to do next? What kind of mind unlocks the forces of the sun and then builds both bombs and hospitals with it? We're still learning how to live with that power, still learning how to balance curiosity and caution, ambition and restraint. But one thing is certain: once we opened the atom, we could never close it again. In every reactor core, in every medical isotope, in every fusion experiment striving to light our future, the heart of the atom continues to burn. And we, the curious apes who dared to look inside, must decide how that fire is tended. Not so long ago, atoms were whispered about in dusty lecture halls and scribbled into the margins of notebooks by curious minds who dared to imagine the invisible. They were theoretical constructs, abstract ideas, philosophical guesses wrapped in Greek robes or sketched out by chalk-stained hands. But today, atoms are no longer just imagined. They're engineered, manipulated, coaxed, prodded, and read like an open book. In a strange twist of history, the tiniest building blocks of the universe now sit at the heart of some of our most advanced technologies. The atom, once elusive, is now a familiar tool in the modern scientist's kit, and the world built around you hums with its influence. Take a deep breath, stretch your arms, and look around your room. Somewhere nearby, likely within reach, there's a device that depends on semiconductors. Your phone, your laptop, your tablet, your microwave. Semiconductors are the reason modern electronics exist. And semiconductors are only possible because we've come to understand atoms not as solid billiard balls, but as quantum objects whose behavior is delicately shaped by energy levels and electron configurations. Silicon is the most famous of these materials, thanks to its unique ability to conduct electricity only under certain conditions. Engineers learned how to dope silicon, introducing tiny amounts of other elements like phosphorus or boron to tweak its electronic properties. This is not casual chemistry. It's the careful crafting of atomic neighborhoods. Entire cities of transistors are etched into slivers of silicon so small they make a grain of rice look like a skyscraper. And each transistor is a tiny gate flipping between states, guiding the flow of electrons that power everything from streaming music to landing spacecraft. All of it is possible because we've learned how atoms behave when packed together, how electrons jump between energy bands, how atomic scale impurities can alter conductivity in profound ways. We didn't just imagine the atom, we learned how to program it. The marvels don't stop with phones and laptops. Step into a hospital and you'll find another world of atomic wonder quietly at work. Magnetic resonance imaging, MRI, relies on the magnetic properties of atoms in your body, particularly hydrogen. Your body is mostly water, and water is full of hydrogen. When you lie inside an MRI machine, a powerful magnetic field lines up the tiny magnetic fields of the hydrogen nuclei, like compass needles. Then a burst of radio waves flips them. As the nuclei relax back into alignment, they release signals that are picked up and turned into incredibly detailed images of your soft tissues. It's not magic, it's nuclear physics. But don't worry, there's no radiation involved. The nuclear in MRI refers to the nuclei of atoms, not anything explosive. It's a stunning example of how knowledge of atomic spin and energy states has been harnessed not for destruction, but for diagnosis. And speaking of medicine, atoms have taken on yet another role as messengers and healers. In nuclear medicine, radioactive isotopes are used to trace the pathways of molecules in the body. Want to know how fast a tumor is growing or whether a patient's thyroid is overactive? Introduce a carefully chosen isotope, track its decay, and measure its signals with detectors. It's like sending in atomic reporters, each one whispering back vital information before fading into the background. In some cases, these isotopes aren't just observers, they're also treatment. Radioactive iodine, for example, is used to destroy overactive thyroid tissue. Other therapies target cancer cells with beams of radiation or implant radioactive seeds directly into tumors. The energy locked in the nucleus, once feared for its destructive power, is now a precision instrument in the fight to preserve life. But perhaps the most thrilling frontier in our relationship with atoms is how we're starting to build with them. Literally. Welcome to the world of nanotechnology. Nanotechnology operates at the scale of nanometers, a billionth of a meter. That's roughly the width of a few atoms placed side by side. At this scale, matter doesn't behave the way you'd expect. Gold, for instance, turns red or purple. Carbon can be transformed into tubes stronger than steel or sheets more conductive than copper. Forces that are negligible in the macroscopic world, like van der Waals interactions or surface tension, become dominant. Gravity, by comparison, almost disappears. Researchers are designing drugs that can seek out specific cells, materials that repair themselves, and fabrics that repel stains, not through chemistry, but through nanoscopic surface structures. In laboratories around the world, engineers are manipulating individual atoms using tools like scanning tunneling microscopes, which let you feel the surface of a material one atom at a time. It's craftsmanship at the scale of molecules. And while nanotech continues to develop, the horizon is already widening further into quantum computing. Traditional computers work in binary. Everything is either a 1 or a 0, on or off. But quantum computers, built on the rules of quantum mechanics, use qubits, quantum bits that can exist in multiple states at once, thanks to superposition. A qubit isn't just 1 or 0, it's both, until measured. Even more powerful is entanglement, a bizarre phenomenon in which qubits become linked so that the state of one instantly influences the state of another, no matter how far apart they are. This opens the door to computations that are staggeringly fast, solving problems that would take classical computers longer than the age of the universe to finish. And what are these qubits made of? Sometimes trapped ions, sometimes superconducting circuits, sometimes photons. Always atoms, or the quantum fields that govern them. The smallest units of the universe marshaled into a new kind of thinking machine. Quantum computers are still in their infancy. They're delicate, error-prone, and famously finicky, but they represent a new way of engaging with the atom, not as a particle or a wave, not even as a metaphor, but as a computational tool. We're not just observing quantum weirdness, we're beginning to use it. In all of this, atoms are no longer the end point of inquiry. They're not just the fundamental building blocks we hope to find at the bottom of everything. They're platforms, gateways, dynamic participants in technologies we're still learning to invent. Our understanding of them has moved beyond what they are and into what they can do. We now think in terms of probability clouds, tunneling effects, quantum coherence, and spin states. Atoms are not just objects, they're possibilities. They're invitations to think differently about matter, energy, and information. They are little puzzles we can shape, tools we can wield, and canvases we can paint with forces invisible to the eye.
Even in areas like agriculture and food preservation, atomic techniques are quietly at work. Radiation can sterilize medical equipment, kill bacteria in food, and even help trigger genetic changes in crops to boost yield and resilience. In archaeology, carbon dating based on radioactive decay lets us look into the past with unprecedented clarity. And in space exploration, atomic clocks using the oscillations of cesium or rubidium atoms allow for navigation so precise that your GPS knows if you took a wrong turn at the coffee shop. Those same atomic principles make up the beating heart of interplanetary probes, guiding them through the silent void with exquisite accuracy. So, here we are, floating on a planet wrapped in technology that hums with atomic elegance. From the chips in our phones to the isotopes in our scans, from nanobots in the lab to the glimmering future of quantum processors, we live in a world built from the inside out. A world where atoms are no longer mysteries to unravel, but materials to sculpt. We've come a long way from Democritus and his invisible bits of matter drifting in the void. The atom has become both more real and more abstract, more solid and more slippery. It's not the end point of understanding, it's the entryway into a deeper, more powerful, and often stranger engagement with the universe. We've learned to listen to atoms, to speak their language, and to dream in their patterns. And now we're beginning to build our future with them, one quantum possibility at a time. After all our chapters, experiments, equations, explosions, and quiet revelations, we come full circle to the atom. That ancient idea, once imagined as a perfect, indivisible seed of matter. From the musings of Greek philosophers to the edge of quantum computing, the atom has remained both a cornerstone of our understanding and a bottomless well of mystery. We started with the word átomos, meaning uncuttable. But as it turns out, the atom is anything but solid and final. We cut it, and inside we found a nucleus. We cracked the nucleus and discovered protons and neutrons. We probed further and found quarks, gluons, fields, and fluctuations. And just when we thought we were at the bottom, the floor gave way again, revealing that even the very space between things hums with activity, virtual particles flashing into and out of being like fireflies in the dark. The atom is no longer a thing. It's a story, a pattern, a wave of possibilities dancing through time and space, a cloud of maybe shaped by probabilities and held together by forces we've learned to describe but not fully explain. What once seemed like the final word in matter has become the starting point for questions deeper and stranger than the minds of ancient philosophers could have ever dreamed. It is humbling, really. We used to picture atoms as little marbles, tiny, indestructible, perfect. Now we see them as smudges of likelihood, bits of energy, interactions between invisible fields. Even a single electron is no longer in a place, it's probably somewhere, until you look. And even then, it's not so much there as it is a result of the act of asking. And yet, despite all this uncertainty, all this quantum ambiguity, the world holds together. Atoms form molecules. Molecules form cells. Cells build forests and cities and curious humans who sit quietly and wonder where it all came from. We are made of this same dust, this same energy, these same fields.
You and the pillow beneath your head are woven from the same invisible threads. What a tender thought, really, that we are not merely in the universe, we are the universe in a very local, very sleepy form. The atom teaches us that the smallest things are not always simple, that what's invisible is not empty, that mystery is not a failure of understanding, but a quiet invitation to keep exploring. From ancient alchemists dreaming of hidden essences to modern scientists firing particles through vast underground tunnels, we've been asking the same questions over and over. What is this world made of? What holds it together? What's beneath the surface? And how deep does the rabbit hole go? Maybe that's the most beautiful part. The questions haven't changed, even as the answers have become richer, more complex, more delicate. We're still peering into the unknown, still brushing up against wonder, still learning to ask with both curiosity and care. And now, as the day slows and your breath softens, let the thought of the atom settle around you like a blanket. Know that every breath you take is a choreography of atoms, oxygen gliding through blood, carbon flowing from cell to cell, tiny messengers of matter doing their ancient work. You are made of the star's leftover pieces, fused in furnaces billions of years ago, scattered across galaxies, and gathered now in this quiet moment of rest. What a gentle, impossible thing to be composed of particles forged in the heart of exploding suns and to lie here, listening, wondering, drifting. So, as your eyes grow heavier and your thoughts begin to wander, remember what we asked at the very beginning. What is this world made of? What strange secrets sleep beneath the surface of matter? And the answer, perhaps, is that the universe is made not of things, but of whispers, of vibrations, of fields, of dreams too small to see, but too essential to ignore. The universe is not a machine, it's a quiet song, and atoms are its notes. Sleep well, fellow traveler of the small and strange. May your dreams be full of hydrogen and stardust, uncertainty and wonder. And may you wake tomorrow still asking questions, still listening for the soft hum of the atom beneath everything. Good night from the Midnight Scientists.